All right, so the first return problem. This is where we're starting today, really. So what's the probability that in one dimension you get back to the origin for after t time steps, right? That's going to be a little thing to work on here. So we've shown that random walks, it's this really fundamental thing underneath them, diffusion, right? So Einstein's 1905 paper showing atoms exist. And then Gaussians come out of it. Those things are universal. I mean, this is a really big deal, right? Right? If we meet aliens and they're kind to us, then lots of things we'll have all sorted out, right? And we'll be primitive, I guess, but the Gaussians will be a big part. There'll be heptapods, maybe. Yeah? No? Arrival fans? Okay. Let's see. So will our drone can always get back? And what happens with dimensions? What about if they're on a network and so on? Okay. So we're going to find something with an interesting exponent. And I think that's just a nice piece. Some physical structures can arise from randomness, so there's that. So how are they structured? And then you can deviate from randomness to superlinear and sublinear scaling structures. All right. And there's a little piece that I want to add in here, and I won't go into too much, but it's scaling relations. So that if you have systems with more than one exponent, for whatever reason, then often they're related by simple algebraic connections. So that's a powerful thing to figure out. Okay, so let's work through an approach to thinking about this. So this is a random walk in 1D, so it's ending up down here. And so it's got a number of first returns, right? So this is a first, this would be a first return. This is now just a return and a return. But if we start again, this is a first return relative to this one. This is a first return. So in one set, right? Yeah. But if little simulations, an easy whatever system you use, you just write a little bit of code, plus or minus 1, add them up. And then, when do you get back to 0? Record that, and then keep doing it, and get a histogram, and see what you end up with. So, small point is that we can only get back to the origin when we've had an even number of steps because of the nature of this thing. You can generalize random walks to be, to have funny numbers of steps and all sorts of things, but this is what we have. So these are just returns, as I said, at 8, 10, and 14. So we want a first return, so we'll FR for that, so it's going to be first return. So it's a probability to get first return at t equals 2n. So probability calculations, you can often turn them into just counting things. They're both, right? These things go back and forth, and statistical mechanics is full of that. Combinatorics is full of that sort of thing. So this is very nice, just super counting, just counting stuff. That's what we're doing. With some weird things. All right, so we're going to transform this problem into an easier return problem. The return problems are not so bad. In fact, we've already solved it, right? What's the number of walks that get to here? It's 2n choose 2k. We had that result before. And where k is n over 2, right? So we had 2n choose 2k. That's the number of walks that go k this way or whatever you want. And so we could, right, so it's in the middle of that. It's going to be 2n choose n. Right? That's the middle of this binomial distribution. Okay, oof, that thing is toxic. Okay, wow. All right. So let's do something slightly different. So this is just an example of a pure first return, right? So let's just look at it has to be a first return. So if it's a first return after this, just in this example, 16 steps, then it could go either way. So it's true, there is a step down. So we'll just ignore that for a second. The first step has to go one way. So we'll say it goes to 1. That means the last step here would have to start at 1, right? Because we're saying it has to get back at 16. And this is an example of a number of walks that can do this, right? So there are walks that keep going up, right? Or maybe go a different way here, but this is just one example. But it has to have this piece here and this piece here, and in here it can only come back to 1, right? It can never hit here. So that's an important feature of this thing. Random walks are exciting. Right? So that's a big deal. So it can't hit here. So if we look from here, right, and that's what this is, if we look from here across, now we have a walk that has some returns to the origin. That's a little bit easier to handle. Okay, that's what this is saying. Okay, so we can deal with, we could say, all right, this is a slightly different problem. We want walks that, if we call this the origin, we want walks, or we say this is just one, we want walks that stay above or equal to 1. That's a little bit less restrictive. So we can do that. And so there's a couple of pieces in here. So probably that we have a first return after 2 n steps. It's probably that our little walk is greater than or equal to 1, right? Through that whole time, from 1 to 2n minus 1 for time steps. We have to be at 1 here and here. And there are a couple of pieces in here. There's half a chance that this walk goes this way at the end. So that's what that half is. And then the 2 is because we need the negative version, the flip. So this is just a little extra counting that balances itself out. So a few little factors of 2 that we have to worry about. Okay. Okay, so that's what that says. All right. Good. So we're going to count numbers of walks, and we'll get back to probably at the end. So we had this piece that you've had to derive. So this is the number of walks from I to j, taking t time steps. We'll do something. We want ones that stay above. Right? We said we want ones that stay at or above, but let's just take all of the ones that go between here and here. It doesn't matter where they go. Let's just take all of those to start with. Right? That's what this line is saying. So we're going to take every path that starts at 1 and ends at 1, and has had this many time steps. So if we can find the ones that go wrong, if we can so this is counting all walks that do basically what we want, except it's also counting the ones that go on. If we can find a way of accounting for them, then we can subtract them off and we're in good shape. Lots of words. Right? We'll call these excluded walks, the ones that go below 1. So I'll have some more pictures. So it's called a method of images to get to these things. So here it is. All right. You can go back to that slide maybe if you want. So here's an example walk that starts at 1, ends at 1 within this, these are cutoffs, well, 16, right? So we're imagining it's a first return walk, went to here. So this is a bad walk, right? Because the black one I'm talking about, it went underneath our line here. So we can identify another walk that starts at -1 and ends at 1 and traces out the mirror of this until it hits 0 for the first time. So you have to think about this a little bit. All right, so the one in black is a bad walk. It's one we want to exclude. We want to say, okay, we want to be able to count this and say that it's not doing what we want. We only want walks that can hit here and then stay above. All right, so what we do to construct a version of it was we say, okay, let's flip the part of the walk that up till its first time that it hits 0. Flip that, and then that's this blue one. Okay, so how does that help? So because the idea now is if we think about all the walks that go from -1 to 1 and then flip, they have to cross the origin at some point. So if we start with the blue one and then flip it up, then we make one of these bad walks, right? So and then you can think about this. Every possible walk that's bad can be made exactly from one of these walks that starts from -1 and 1. Right? So -1 to 1, it has to cross the origin somewhere. Where it does the first time, we take that part of the walk, flip it up, color the whole thing black, and that identifies one of these bad walks, right? We only want walks that stay above here because we're thinking about walks that do not return until here. Here's another example. So this is truly a bad one, right? Because it hits here and it stays below and then it gets back to 1. This is the black one. So, but that would be exactly made out of this blue one. It first hits the origin here, flip that part up, and it makes this one in black. And that's another walk we'd like to exclude. So that's the idea. For every bad walk, there's a matching one in blue that starts at -1 and ends at 1. So you need to think about this. So the idea is we could count every walk that goes from 1 to 1 and then subtract every walk that goes from -1 to 1. And the every walk calculations are easy because they're of this form. They're just binomials. So it allows us to you know, you have to see this, you have to create this thing. It's used in a lot of different ways, this method of image. Lots of different things in physics in different circumstances, but this is this is some cleverness, right? This is one of these things where a lot of monks died to figure this out, right? Okay. They went crazy, right? And eventually, one very smart monk called Euler probably figured it out, and then all the other monks felt bad. But yeah. So we do a terrible job in science by not having most of our journals filled with things that where nothing happened, because that's really what science is full of, right? So we have just this sort of little crust of stuff that seems to be exciting and interesting, and the p-value was less than 0.05. There are fantastic plots, where people have gone through all these papers and found out all the p-values, and they all cluster around 0.05, just as they naturally would. And then another little bump around 0.01, yeah. Okay, so, point is, this is a hard thing to get to, but once you have the plan, it's a calculation problem. But it's a good thing to think through and get into your mind, but we're not driving it from, I didn't just hand you this and say, figure it out. Okay, so we're going to have these two pieces. There's going to be the number of walks that go from -1 to 1 over some number of time steps t, and then we'll just have number of walks that go from +1 to 1 time step t. So we'll need those. And that's this construction. If you can see it, I know it's at the bottom. So the number of first return walks, and this is the number, start at 1, end at 1, takes this many time steps. The number that start at -1, end at 1, takes this many time steps. Because this thing, which is just walks from -1 to 1, turns out to exactly account for all of the bad walks in here. That this one is counting and we don't want to count. All right. So this is a nice construction. As I said, these things are, you can work with them. And so you play with some binomials, add them together. So what you want to do is combine them together, and then you'll have factorials over factorials, have big fractions, and then it's Stirling's approximation, which is fun. I remember so if there were 4 of us who worked together in college and university, and one of them is now on Wall Street from this is from Melbourne Uni. I remember, so his dad was a professor, right, which was a very strange, because I come from a farm, right, and so I remember we were at his place one day, and his dad just said, "Oh, that's Stirling's approximation." Like, he knew all these things. I'm like, what are you? This is cheating. Okay, anyway, so it's a beautiful thing, just like factorials. Okay, so actually this is what you get out, which is crazy. There's a root pi will pop in here. So it's all normalized properly. You don't have to worry about this too much, but this is really the key little beast in here. So we're going to normalize it. This is the total number, and the total number of walks grows ridiculously because we're allowing all possible ones, branching, 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 branching. Right? So we get 2 to the power of 2n. So we have to divide by that. That's how many paths we've allowed. Got this crazy thing going on, exponential growth. So if we divide through by the 2 to the 2n, that's what we're doing here. So this is just going to be clean up. These things will go away. And if you want, you can put this, there's a 2 to the 2n, that's going to cancel it, but there's a -3/2. So we're going to stick it with that one. That's good. And when we clean all these things up, we're going to end up with a √2π, which is the correct normalization for this thing. And this is really length, right? So this is 2n. As I said, it can only be even numbers. So that's what we did. This is really time, right? So it's time to the -3/2. Very exciting. So you have to get to that point. But time to the -3/2. So this is an exponent between 1 and 2. T to the minus, right? 3/2 between 1 and 2. And we now have a feel for this. It's normalizable, right? There's not too much room in this tail, but the mean is infinite. And this is something that there's no upper limit to it. As random walks, it's a mathematical thing. So the mean is truly infinite. All the moments are infinite. So that's pretty weird. So I have these things, right? So it's normalizable, which means that the random walker will always come back. So it's recurrence. So you always get, even with the gambler, if you're doing this, you always get even eventually. But you will run out of existence, which is a problem. So if you get behind, just walk away, right? Anyway, so all these high moments are infinite, which is weird. So we expect a long wait. So yeah, don't do that against an infinitely wealthy opponent. Higher dimensions, much hard work to do. This is a different game. Polya figured this out. So 2 dimensions, your random walker will always come back still, and it's also, of course, infinite for the average time. But once you get to 3 and above, then they can escape or never return. Your texter may never come back. And so now you've just got more ways to leave the world. So if you have an infinite dimensional network, it depends on the average degree of nodes and so on as to how fast it can escape. But you can see this kind of grows in a bad way, right? So you've got 50% chance of coming back straight away in 1 dimension, and then in 2 dimensions, now it's a quarter because it steps out, and then there's 3 choices and 1 choice to come back, and that keeps growing. All right. Polya did this. So we'll talk about urn models later on, which has a terrible branding, urn models, but it's actually about putting balls in urns. But maybe it needs an update in framing. But the idea is, you put colored balls in them and pull one out and do funny things with it and see what sort of statistics you get with those things. But he's famous for that and many other things. All right, so that's just a beautiful thing that pops out of random walks.